All right, in this video, we're going to review sigma notation, also called summation notation, and it's just going to be a brief overview geared towards the calculus student. All right, so a convenient way of writing sums uses the Greek letter capital sigma, which looks like this. That's capital sigma. And this is called sigma notation. And you can write a sum. This number at the bottom, I equals m, tells us where to start our sum. The sigma means add things up, sum it up, and then the number at the top, n, tells us where to stop. All right? And then typically we denote the general term as a sub I. And so if I were to expand out this sum, I would list out starting at m, a sub m, plus, right, since I have sigma, that means add up these terms, a sub m plus 1 plus a sub m plus 2, and you keep going, and the last term is going to be a sub n. All right, I is called the index of summation. And you may see other textbooks use k or some other variable, but typically I and k are the most common. Okay, a couple important properties that we want to establish before moving forward. First one is if you have the sum I equals m to n of a constant c times a sub I can pull the constant outside of the sum and I will have equality. Okay, so c is a constant. Basically, you can factor a constant out of a sum and you'll get the same result. Also, we can distribute a sum over addition and subtraction. So if I have the sum I equals m to n of a sub I plus b sub I can write this as the sum I equals m to n of a sub I plus the sum I equals m to n of b sub I. Similarly, I can distribute the sum over subtraction. So you can have the sum I equals m to n of a sub I minus the sum I equals m to n of b sub I. All right. Couple more useful formulas here. First one is the sum I equals 1 to n of 1 is equal to n. If you think about it in expanded form, what this sum is telling me to do is to take 1 and add it to itself n times. So clearly that's just going to be n times 1, which is n. All right, I can build on this, and then we have that the sum I equals 1 to n of a constant is equal to c times n. Since we know we can pull the constant outside from earlier, then you would have n, and that based on the property before, times c. So c is a constant. Because in expanded form, again, this just means you take c plus c plus c n times, which would be c times n. All right, next one is my personal favorite. If you have the sum I equals 1 to n of I, that can be computed by taking n times n plus 1 over 2. All right, and so in expanded form, you're starting at 1, so this would be 1 plus 2 plus 3 etc. up until n. And so this gives us n times n plus 1 over 2. And there's a little story that goes around about young Gauss when he was in school, and apparently his class was being very naughty, which is typical. And the teacher, just to keep them all occupied, told them to sum up the numbers from 1 to 100. And little Gauss, he was done in just a matter of minutes, and the teacher was astounded. And so little Gauss explained, he just took 1 plus 100, well, that's 101. Then he took 2 plus 99, that's also 101. And then he realized he had 50 of these pairings, right, of 101. So basically he came up with the formula here, because you take the first term, which is going to be 1, the last term, which is n, that's that n plus 1 that we see in the formula right here. That's n plus 1, 100 plus 1. And then you multiply by n divided by 2, right? Because you have 50 pairings like that, which is right here. Okay, and every time I remember that story, it helps me remember the formula better. All right. Now, next one is for the sum. I equals 1 to n of I squared. And this is equal to n times n plus 1 times 2n plus 1 divided by 6. So in expanded form, this would be 1 squared plus 2 squared plus 3 squared all the way up to n squared. All right, and instead of sitting there and computing that sum, you can use the summation formula. I don't have a cool story for you, sorry. One thing to notice is on the right-hand side, when you expand out the numerator and multiply, you're going to have n cubed, and that's 1 degree higher than the power I is raised to. And then same thing here, this would give you n squared in the numerator, and this is just I to the first. These are going to be really useful for evaluating some of the areas and doing the limits that you need for section 5.2. So I got one more for you. The sum I equals 1 to n of I cubed is going to be n times n plus 1 all over 2 squared. All right, so that would be the sum for 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed. All right, good. Now that we have all those formulas out of the way, let's just work on familiarizing ourselves with sigma notation. Perhaps it's been a while. So example 1, write in expanded form. So we have the sum, I equals 1 to 5 of the square root of I. Okay, so I is just the index of summation. Don't start thinking imaginary numbers. We're just going to write it in expanded form. So the first term is going to be square root of, I'm starting here at 1, plus, and then I'm going to fill in everything up until 5. That's the last number I'm going to substitute in for I. So rad 1 plus rad 2 plus rad 3 plus rad 4 plus rad 5. And we're done. We were just asked to write it in expanded form. So stop there. Okay, next example. Write in sigma notation. So go the other way. And this time we're given the sum. 1 plus 2 plus 4 plus 8 plus 16 plus 32. And it stops there. So let's see, can we identify a pattern between the terms? I noticed to get from one term to the next, I'm multiplying by 2, right? And in fact, each of the terms is a power of 2. This is 2 to the 0, 2 to the first, 2 squared. Do you see it? 2 cubed, 2 to the fourth, 2 to the fifth. This is a geometric series. And you have several ways you could write out your sum, So you could either write it as the sum, starting your index at 0, ending at 5, and you would have 2 to the I. That's one option. Or if you don't like starting at 0, no problem. You could still start at 1. Then you'd have to go up until 6, and your first term would be 2 raised to the I minus 1. That way it still comes out to be 1. So either one is correct. It doesn't matter. Okay, good. Let's look at another one, maybe a little more exciting. Example 3. We're going to write in expanded form. And here we're going to switch the index using k equals 0 to 4, doesn't matter. Then we have 2k minus 1 over 2k plus 1. All right, so for this sum, I'm going to start by substituting in 0 for k. So we're going to have 0 minus 1 over 0 plus 1 plus, now substituting in 1 for k, I'm going to have 2 minus 1 over 2 plus 1. Then I'm going to plug in 2 for k, so 4 minus 1 over 4 plus 1. Then 3, so 6 minus 1 over 6 plus 1. And then I'm going to stop at 4, so 4 times 2, that's 8 minus 1 over 8 plus 1. All right, and then let me just simplify each of these terms, and I'll be done. So I'll have negative 1 over positive 1, that's negative 1, plus this is going to be 1 over 3, plus this is 3 over 5, plus 5 over 7, plus 7 over 9. So that's our final answer there. Okay, looks good. Now let's apply some of those summation formulas that I gave you earlier. This is going to be useful in some of your calculus problems. So find the sum or find the value of the sum. So we have the sum I equals 1 to n of I cubed minus I minus 2. Now notice the upper limit or the upper bound is a variable n. So our answer is going to be in terms of n. You're not going to get an actual constant for your sum. So we're going to use our summation formulas. First property I want to use is I can distribute this sum right across each of the terms. So I can rewrite this as the sum I equals 1 to n of I cubed minus the sum I equals 1 to n of I minus the sum I equals 1 to n of 2. And then based on the formulas that I listed earlier, I can replace the sum I equals 1 to n of I cubed with n times n plus 1 over 2 squared minus, now this sum, that's the one little Gauss came up with, so we have n times n plus 1 over 2 minus, and then remember a constant summed from 1 to n is just going to be the constant times n. Okay, now it's up to me to clean things up a little bit. So let's see, what can I do? Well, I can distribute this exponent inside, all right, and down here too, don't forget about that. So we'll have n squared times n plus 1 squared over 4. And then looking at things, I'm going to want to get a common denominator. So let me multiply the second term by 2 over 2 and the last one by 4 over 4. So then now I'm going to have minus 2n times n plus 1 over 4 minus 8n over 4. All right. And then now I can write everything over the same denominator and then just work on simplifying all the terms in the numerator. So I'm going to have n squared times n squared plus 2n plus 1 minus 2n squared minus 2n minus 8n all over 4. And then I can distribute some more, so we will have n to the 4th plus 2n cubed plus n squared minus 2n squared minus 10n over 4. And then, let's see, I can combine some like terms here. So we'll have n to the 4th plus 2n cubed minus n squared minus 10n over 4. And one thing I noticed is I can factor out an n from each of the terms in the numerator, and we want to go ahead and do that. So we have n times n cubed plus 2n squared minus n minus 10 over 4. Yay, there's our answer. So let's box it. Ooh. And that concludes that example. All right. Next one, example 5, asks us to evaluate the telescoping sum. Now this is something you're going to need, especially when you study sequences and series in Calculus 2. So a telescoping sum is one where a lot of the terms in the middle collapse, like a telescope does when you close it. So we have the sum I equals 1 to n of I to the 4th minus I minus 1 to the 4th. And the way to evaluate it is you just start listing out the first few terms and see what sort of pattern emerges. Okay, so I'm going to start with I equals 1. So this is going to give me 1 to the 4th minus, if I'm substituting I equals 1, I'm going to have 0 to the 4th, right? So this is for I equals 1. Plus, now if I substitute in I equals 2, I have 2 to the 4th minus 2 minus 1, that's 1 to the 4th. This is I equals 2. Plus, let's keep going, I'm going to have 3 to the 4th minus 2 to the 4th, that's I equals 3. And then you can see the pattern's going to continue. And then let's list out the last 3 terms as well. So the last term would be I equals n. The one before that would be I equals n minus 1. So let's start maybe with I equals n minus 2. So I equals n minus 2, we're going to have n minus 2 to the 4th plus, minus n minus 3 to the 4th. That's for I equals n minus 2. Plus, if I'm substituting in n minus 1 for I, I'll have n minus 1 to the 4th minus n minus 2 to the 4th. This is for I equals n minus 1. And then my last term would be I equals n. So I'd have n to the 4th minus n minus 1 to the 4th. Now notice here, this is where the fact that the sum is telescoping comes into play. I have positive 1 to the 4th as my first term, and that's going to cancel out with this negative 1 to the 4th. And then 2 to the 4th is going to cancel with this negative 2 to the 4th. And then you could imagine the next term, I would lose 3 to the 4th. So what's the only term that didn't cancel out? This negative 0 to the 4th. So I had one term not cancel out in the beginning of the sum. That means I should have one term also not cancel out at the end of my sum. So let's see here. I have n minus 1 to the 4th, a negative n minus 1 to the 4th, and that's going to cancel with this positive n minus 1 to the 4th. I have negative n minus 2 to the 4th, which is going to cancel here. And then n minus 3 to the 4th would cancel with the previous term. So what's the only term that didn't cancel out? N to the 4th. So that's why it's called telescoping, because only a term or two at the beginning of the sum and a term or two, it could be a couple, at the end of the sum will survive. and then all of the terms in the middle collapse. And however many terms don't cancel out in the beginning will match the number of terms that don't cancel out at the end. All right, so what are we left with? All I have is 0 plus n to the 4th, which is going to be n to the 4th. All right, looks good. Let's work on another one. That was really fun. So example 6, another telescoping sum. So evaluate the telescoping sum. So here we have the sum, I equals 3 to 99 of 1 over I minus 1 over I plus 1. So in this case, my upper limit is 99, it's not n, but we're going to set up the problem in the same way. So let's start off by listing the first few terms. I'm starting at 3 this time though. So I'm going to have 1/3 minus 1/4 plus 1/4 minus 1/5 plus 1/5 minus 1/6 dot dot dot. And then the last few terms are going to be, well, I end at 99, so let's do the last 3 terms again. So we'll have 1 over 97 minus 1 over 98 plus 1 over 98 minus 1 over 99 plus 1 over 99 minus 1 over 100. All right, well, let's see. What cancels out? 1/4 is gone. 1/5 is gone. And I know that negative 1/6 would be gone, right? And then for the last few terms, 1 over 99, 1 over 98, and then 1 over 97 would cancel out. So all I'm left with is 1/3 and negative 1 over 100. And you have a feeling that one term is going to survive at the beginning and the end of the sum, because see how I and I plus 1 are 1 apart? That tells you basically how many are not going to cancel out. So now I'm going to be left with 1/3 minus 1 over 100, and then if I get a common denominator, that's 100 minus 3 over 300, so the sum is 97 over 300. Okay, looks good. Now let's work on evaluating some limits involving sigma notation, much like what you're going to be expected to do for some of your calculus problems involving areas. So example 7, find the limit. So you're given the limit as n approaches infinity of the sum I equals 1 to n of 1 over n times I over n squared. Okay, first thing I want to do is clean up the expression as much as possible. So I can rewrite this as the limit as n approaches infinity. Now, I is my index of summation. N is just a constant, which means I can pull out 1 over n outside of my sum. And in fact, this is going to be I squared over n squared. So I could also take out that 1 over n squared, right, since that's a constant as well. And then I have the sum I equals 1 to n of just I squared now. All right, that looks good. So now this is the limit as n approaches infinity. These two I can clean up, multiply by each other. I have 1 over n cubed, and then I'm going to replace the sum I equals 1 to n of I squared with the summation formula I listed above. So remember, that's n times n plus 1 times 2n plus 1 over 6. So I'm evaluating the limit of all of this. Okay, first let's start off by cleaning up a little bit. I can cancel out one of the n's. So now this is n squared in the denominator. And then I'm going to have the limit as n approaches infinity. Now let me multiply out what's left in the numerator, just n plus 1 and 2n plus 1. That's going to give me 2n squared plus 3n plus 1 over 6n squared. And then if I take this limit as n goes to infinity, since the degree of the numerator is equal to the degree of the denominator, the limit's just going to be the ratio of the leading coefficients, 2 divided by 6. So this limit is 1/3. All right, good job. Let's do one more to conclude the lesson. So same directions, example 8, find the limit. So we have the limit as n approaches infinity of the sum I equals 1 to n of 2 over n times the quantity 2i over n cubed plus 5 times 2i over n. Okay, so start the way we did last time. I'm going to take this constant outside of the sum. So this is equal to the limit as n approaches infinity. We have 2 over n times the sum I equals 1 to n of 2i over n cubed plus 5 times 2i over n. All right, can I clean up my sum a little bit more? Can I pull out any more constants? Well, I notice I have 2 over n cubed and then another 2 over n here. So I can take out a 2 over n. Why not? Let's clean things up. So now I have the limit as n approaches infinity. I have 2 over n times another 2 over n that I factored out. And then I'm left with the sum I equals 1 to n. Now what am I going to be left with? I took one of the 2's out, so I'm just going to have a 4i cubed over n squared. Remember, I took 2 over n out of that term, plus 5i, since I factored out the 2 over n. Okay, now similar to last time, I have the limit n approaches infinity. This is going to be 4 over n squared. And then now I'm going to distribute this sum across the terms and also pull out whatever constants I can. Okay, so I'm going to write this as 4 over n squared times the sum I equals 1 to n of I cubed plus, let's take out that 5, the sum I equals 1 to n of I. Nice, so things are coming along. Now we have the limit as n approaches infinity of 4 over n squared times, so we still have 4 over n squared. I'm going to replace the sum I equals 1 to n of I cubed with, remember, we have n times n plus 1 over 2 squared plus 5 times, and then this sum here, remember, I can replace with n times n plus 1 over 2. Ooh, all right. Now let's start cleaning up. So what do I notice here? We have the limit as n approaches infinity. Let's just leave this 4 over n squared here. I notice I can take out n times n plus 1 over 2 from each of these terms, right? So I'm going to have n times n plus 1 over 2 times, well, what's left over here? I'm going to have 4. I still have an n times n plus 1, because remember it was squared in this term. N times n plus 1 over 2n squared plus, now just 5 is left over in the next term. All right. Now from here, what can we do? Well, we can start canceling some stuff. So I have the limit as n approaches infinity. So we have here 4 over n squared times n plus 1 over 2. And then let's get a common denominator and clean up this expression here. So we're going to have 4n squared plus 4n. If I get a common denominator 5, multiply it by 2n squared, it's going to become 10n squared. And this is all over 2n squared. So now let's see, what can we cancel? Well, I can cancel out the 4 with these two 2's down here. And also, this n cancels out. Let's do a different color. This n cancels out with one of the n's in the denominator. All right, so what are we left with here? So now I have the limit as n approaches infinity. I've got an n plus 1 left in the numerator, a 14n squared plus 4n, and n cubed in the denominator. All right, I can see the light at the end of the tunnel. So this is the limit as n approaches infinity. Multiplying out the numerator, we'll have 14n cubed plus 18n squared plus 4n over n cubed. Degree of the numerator equals degree of the denominator. So you're just going to take the ratio of the leading coefficients, 14 over 1, which is 14. And voila, we are done. All right, so that concludes the review of sigma notation. Hope it was helpful. Leave some comments below and let me know what else you would like to see.